Okay. So any final questions before we get into the material for this week? Okay. So we're going to do more on pointers because we know you love them so much. No, actually it's the most important part of this course is understanding memory addresses. And the fact that you struggle with them so much is fine because it's part of the journey. So as we know, pointers are a variable that represents a memory address. Now, we often talk about that we can have multiple levels of indirection. So I can have a pointer to a pointer to a pointer to a pointer to a pointer. It's probably even better to think about it this way. So here I have a pointer to a char, and then I have a pointer to a pointer to a char. And similarly, with the one down below here, really we think about it as we have a type called an int, then we got a type called a pointer to an int, and then when we point to that we have a pointer to a pointer, and when we point to that we have a pointer to a pointer to a pointer. So it's actually just a simple indirection. So yeah. I don't know, Brad. I have known of people use for very, very large multi-dimensional data having an array, having pointers of 100 levels. Yeah, it would. I would actually, as much as possible, you want to simplify your abstractions to be things which are more readable to fellow human beings. Remember that your fellow human, it's more important actually that your fellow human beings can read your code than that the compiler can. Because human beings can fix any problems the compilers are having, but the compiler can't fix any problems the human is having. Well, it's one of these very hard problems. Look, we can't even accurately transcribe a song to notes and duration yet. We can't even do that. So substantial things we can't do yet. Yes, we can actually have machines which generate code which is sent to other machines and only the machines understand it. Sure. But yeah, machines are basically dumb. We are getting smarter at getting them to do things. But anyway. There's I may or may not have mentioned this before. One of my favourite computer scientists, a guy called Donald Knuth, really smart man, way above my intelligence, to be quite honest. He started something way back in the 70s called literate programming, and it's the idea that you actually write your comments and then fill in the source code in between later. So you actually figure out what the program is going to do, and then you write the code to get it to do it. And your main aim is to communicate your intentions to other programmers. I like that. In fact, if you just Google literate programming, you'll probably come up with his website. But there's been lots of technologies based on that, JavaDoc, and so on. Even something called Doxygen, which you can use for C to generate HTML documentation from C. Started from that idea. Anyway, so let's talk about multi-dimensional arrays. In C, when we declare an array on the stack and we give the 2 dimensions, when we pass that array around to other functions, we have to give the size of every dimension except the first one. Anyone know why? Pencil. Let's call this memory, right? It's not so much that, it's let's just say this is an array of some type. How do I know Well, there's a reason why, and we're going to go into that just briefly. How do I know how far I need to jump ahead in this array to get to the next element? The array is some type. Correct, Ross. Size of element. So with an int array, I know that each element is 4 bytes apart. Right? But what if, okay, we now have a 2D array. Now, is this how the array is actually laid out in memory? Anyone know? How is it laid out in memory? All memory is flat, correct. So how does the compiler know? So for example here, we have 0, 1, 2. How does the compiler know where the next dimension is? We need to tell it. That's why, for example, this array here, which is 3 by 1, 2, 3, 4, 3 by 5. So it's actually, let's say if these are ints, it would be int 5, 3, because the height is the first dimension and the width is the second dimension, right? So we need to pass that into the function. So the 3 here tells it, or actually to jump to the next row, you jump ahead by 3 places. 1, 2, so we're at 0, and we just add 3 to it to get to the next row. 1, 2, 3. And that's how, with multi-dimensional arrays, we can actually traverse them. Okay? That's why the first parameter becomes a pointer. So this actually becomes an array of 3 pointers. Which are essentially pointers to the beginning of each row. Oh, yeah? Of each column, sorry. Okay, now it gets a lot easier when we talk about dynamic arrays in multiple dimensions, because we can represent them simply by using pointers. So we could in fact, for a dynamic 2D array, represent that as star star. Much easier representation, where the width and height are actually things we hold in the matrix. And then we malloc the rows first. The width. So there's going to have a whole bunch of pointers. Size of int. Actually, probably we should have done this height, really. But they're doing it the other way. Anyway. And then, so let's actually, to avoid confusion, change these back. Height. Width. So you allocate the array of pointers for all the rows that are going to exist. And then we malloc each row in a loop. And you see how this is in some ways kind of similar to what you're doing in your assignment, except you're going to use a list instead. You've got lines of text as the data elements in your linked list, and you're linking them all up in your list. We'll come back to this if we've got time. I don't think we will, because there's more. Okay, so everyone understands what's wrong with this function, right? Do you understand? Tell me what's wrong. Well, yeah, so we change the variable that's passed in. Right. But this is a copy. This is a copy. You know, we have formal parameter, which is what's declared when we declare the function. But the actual parameter is a copy. So we make a copy of each parameter. And so the copy is a local copy. So when we leave the function, we lose the copy. How do we fix it? Right? Something like this, right? What if the thing that we want to change is a pointer? Correct. Just like you did in assignment 1. Now, this passing of structs by value, also assigning a struct. What happens, as some of you did this in your assignment 1, what happens when you assign a struct to another struct? No. If you assign one struct to another struct, in fact, Ben, you were doing this yourself in the code you sent me. Correct. Each individual value is copied. As long, but what happens if they're pointers? Right, the pointer value is copied. But what happens when they're arrays? Is it something different? Actually, there is. Well, it's more complicated. Say if I've got... Why don't I do this? Array copy. So let's just say I have a struct. Yeah, struct line. And I say in here char text 80 plus 1. These would be hash defined in your code, obviously. And int len. Right? So here, if I in main so struct line A comma B, this is exactly you shouldn't be using variable names like these. I saw some people do it where they had an array called P and I had no idea what it was. This is just a rough example. So let's just say into a dot text hello and a dot len equals strlen of a dot text. Oh sure, I and J are standard iteration names. So I would use K potentially for the next dimension. Correct. There is always a provide, but okay. So %S %D a dot text a dot len. Okay, before I exit I need to have some hash defines or hash includes. Okay. Okay, fine. So now if I run this, okay, nothing surprising there, but watch this. B equals A. just change this to B. And I'll prove to you one last thing. Anyone know what percent P is for? Yep. So I have to cast these to avoid star because that's what yeah. Stupid. So what am I doing on this line? I'm printing the memory addresses. This is to prove to you that I've copied the data, but they are different memory locations. Yes. So you see, they're next to each other, but they are different. Like the first one ends in 34A0 and the next one ends in 3440. In fact, you can tell the size of them from that by subtracting. But anyway, so in fact, when I did this assignment, I make a copy of what's there. And in fact, I could do something like b.len++. So you see, it's a copy. So that's exactly what happens, by the way, when you pass a struct into a function as a parameter. So why didn't I get you to do that in assignment 1, do you think? Why do you think I made you make them pointers? Is it because I'm cruel? No, it's not because I'm cruel, I promise. Well, you're passing in the address of the thing, right? And the address is 8 bytes. And say a move. A move has 1, 2, 3, 4 ints, right? So it's 16 bytes. So in fact, it's cheaper to pass a pointer than to pass the contents. I'm very conscious of the fact I'm looking backwards and I'm looking forward, so I'm trying to teach you some stuff about what you've already learnt, as well as some stuff about what you're going to need to do. And in fact, we can use const pointers if you have a look at last week's list code, you'll see that my person comp function was in fact had const person pointers. And that means that the function they're passed to can't change them. Okay, so what's the change we have to make to this function? Because we agree this is wrong, what's up on the screen, right? Size t is an unsigned int guaranteed to be able to hold the size of any memory. But I wouldn't use them for anything other than actually holding a size, because arithmetic on unsigned is slower, much slower. Takes about twice as many instructions. So what's wrong with this function? Why? You might be right, Brad. Just tell me why. No. The size of is on int. Well, we always have to assign memory to a pointer. Well, no, because the things that they hold are ints. We know how big they are. So, yeah. Okay, we may be you're getting a bit closer. That's not it's not exactly the issue, but it's related to it. What happens to array at the end of this function? Yeah. Remember that all parameters are passed by value. They are copied. So we are assigning to the local copy of this pointer. Which means when we leave this function, the pointer passed in will not have changed. Because all the changes happened to local copies. So how do we fix that? Yes, but in order to do that, the types have to match. So, correct. The type passed in must be a pointer to a pointer. Then and the job's done. You see how now, correct, you're actually changing what is being pointed to. And in fact, this will be called, say in main or somewhere, say we had int start array Then we would do allocate. And let's just say we want tenants. And we can wrap that in an if because it's a Boolean. If not, allocate. And then we'd have an error message. Right? The other option, which some of you hinted at, was in fact leave. In fact, we don't need to pass in array at all. It makes no sense to pass it in. And instead, let's do it here. Int so then we would be returning null, and otherwise return the array. And then we would do some size, say 10. Yep. You can have an opinion about which one is cleaner or whatever, but the more important point is to understand the code in either case. Okay? Okay, so the phases of compilation with GCC. When we compile a program, such as GCC minus ANSI wall pedantic, there's a few things which happen. Each separate file is parsed separately, right? They're parsed and compiled separately into .o files. But even before that, what happens is the preprocessor goes through the file and replaces any of the precompiler directives. So anything which starts with a hash is replaced. And the constants are replaced with their value before compilation. Right? That's why we can't use the debugger with preprocessor directives, because it happens before compilation. And you can see the results of it. I'll do that very quickly, the minus E flag. So we've got this array copy.c, and what I'm going to do is I'm just going to, okay, so this code has been parsed by the preprocessor, and you see we get all of these function prototypes from the header file. We've got to have all of them just in case I might call one of them. But then we've got the stuff in my code, right? So we've got the struct line, and in fact what I might do hash define line len to be 80, And you see that the my hash define has been replaced with the actual value, because that's what happens in the pre-processing phase. Okay, so at the end of it, the end of the pre-processing stage, we have our file with all of the pre-processor directives have been processed. So then, let's go back to my slides. So next phase is a parse each source file. And so we do things like lexical analysis. Lexical analysis is to divide up the code into the symbols of the language. So A equals 3 semicolon. So A equals and 3 and semicolon are all different lexemes. We might do some type checking. We do type checking. Evaluate the syntax, all that stuff. And then we compile that to assembler. And in fact, you can see the assembler. Hang on, let me just... And then we have, should be, there it is. We have the assembler for my program. Now I'm not expecting you to be able to read all this. Actually, I can't, to be honest. I know enough assembler that if I had to, I could learn more. And but you can see here calls to string len and moving of bytes around and all this kind of stuff. This is all that C is protecting you from. Calling of printf. You see, remember how we were saying you move parameters onto the stack and then you jump to where the function is implemented? That's happening there. Anyway, so that's the assembler. And then we can, in fact, the last stage is to assemble that assembler into an object file. So compile only. And in fact, that's what's generated by compilation. Now, this is an ELF file, so it starts off with the ELF code, but I wouldn't worry too much about it otherwise. But the thing is, I want to build a big project. I want to build a project, and I've figured out that you'll probably have at least 1,000 source files. In fact, I don't have it here anymore, but I had a copy of the GCC source, and it had 29,000 source files as part of the project. So I come along and I make one small change. Do I really want to recompile all of those files? Ben actually made you do this from memory in Unix System Admin. Yeah. So if we're only going to change one or two files, we only want to recompile those. Yeah. So that's why we have makefiles. So up till now, we've talked about compilation. But then what happens is that we link the files together with any binary executables, so with any libraries, system libraries, to create an executable. Have any of you seen this kind of a message? Undefined reference to. It's easy to produce. Oh. I just say what I'm going to do is so I've just specified a function that creates a line from a char array. Let's make that more explicit. From a char array. And then what I'll do here is struct line star new line equals create line hello. Rightio. Now if I just do -c for compile only, it warns me about unused variable, but there's no issues. But if let me do this with array copy.o, which was the object file, and I'll output it to array copy. Now part of this is a calling of the linker. LD is the linker, and it said undefined reference to create line, a function that I haven't implemented. And it's correct, it's not, I haven't defined that reference. So that's a linker error, and so that's the last phase. Now why have I gone through all these phases? Well, they have something to do with makefiles. So all those phases we saw, pre-compilation, assembly, compilation, etc. into the .o file, and then all those getting linked together, well, we can talk about them as targets. And targets are essential. So we can have variables in our makefile, and they are the value that a particular variable has. So for example, it is CC, C flags and L flags are some standard variable names. You use those, and make will even help you sometimes. Sometimes it will do the right thing when you've written the wrong thing. Okay? So GCC is the name of the compiler. So that's what we're doing here, as we're assigning that. C flags are the flags that happen with compilation, right? So when you're building those .o files, ANSI, wall, pedantic, and -g are compiler flags, right? They're not linker flags. So you should only have those flags as part of the compilation phase. L flags might be something like LM. By the way, if you're using the address sanitizer, you need to do that as part of compilation and as part of linking. Or it won't work. Okay? And by using standard variable names, if you muck something up, the compiler might do the right thing anyway. Because make is reasonably smart. So then we have targets, right? So for example, for our person lists, we might have a target which is the person list. Now, person list is the target name, colon. Now these are the prerequisites. In order to make the person list, I need to have personList.o, list.o, and safemalloc.o already made for me. And they must be newer than the current version of person list if it exists. Okay? Now, this is what's called the linker target. And we see here that we have a hard tab. This must be a tab. Cannot be spaces. It must be a tab. And so I've got $CC, so I'm calling the compiler. L flags, so the linker flags. And I pass in the object files. -O. Really? Okay. It sounds like my voice is kind of going a little bit, actually. I'm hoping not. I use my voice for a living, so. And any system libraries into a binary called person list. So the compiler targets. So here we have the personList.o. We specify that in order to make personList.o, we need personList.c, list.h, and safemalloc.h. In fact, we probably also need list. Oh, no. For personList.o, yeah. And then to make that, hard tab $CC, $C flags, -C, personList.c, and the output of this will be personList.o. Okay, we can go a step further than this, and we can say person list, it has these prerequisites. Now, hard tab, $CC, the L flags, the input files here are all the prerequisites. $hat means all of those. That's what $hat means, all of those. And $at means the target name. Mind you, if you simply understand everything on this slide and this slide and can do that, you don't need to know what's here. It just makes it, you make files require less effort. If you understand variables. Okay, so just very briefly, I will show you. And we'll have a look in shared, not shred, shared. Okay, so okay. In this case, I have a whole bunch of, say for example, this matrix here requires matrix.o, safemalloc.o. And we call it like, and we compile it like so. Now, I'm going to show you a bit of a change here. I'm going to introduce variables into these ones. So, we're going to $hat minus O dollars at, and I've changed nothing. Okay, and that gets me to compile the text doc program. And what I'm going to do is I'm going to comment out all of these ones which specify that they're targets to build.o files. And I'm going to replace them all with a single target. And these go on for a while. Okay, that's it. And I'll remove these ones too. Oops. Okay. So what I'll do is I'll create a target that is for all .o files. All .o files require a .c file with the same name. And let's just say it will depend upon all header files. So if one header file changes, they all change. We run this. And I think I've got $cc up the top. Let's just see. Oh no, I'll put it there. cc equals gcc. Well, this is C flags because it's compiler flags. Then minus C, the first argument, the first dependency, which is a .c. Alrighty. Make clean, make person list. So that's available in week 8's lecture material. Just very briefly in the last couple of minutes, I'll try and go through a little bit of the stuff on trees. It's important, but it's okay. So far we've been looking at lists with a single pointer. So essentially got pointers to the next node, next node, next node. But that we can actually create something which is really just a modification of that by adding 2 pointers. So instead of a pointer to next, what we have is a pointer to left and right. So what we have is a data structure which starts at a root and fans out. And binary search trees in particular are sorted trees where each node to the left is less in value than any node to its right. So currently we start off with an empty root. Now imagine there's in fact, well, we add a node and see how the node has a left and a right. So currently it has no children, so we only have the root, which is 1138, right? And I just explained this, that anything to the left is less than anything to the right. It's essentially the sorting order. If you're interested in this stuff more, you might be interested in the C++ course, which I also teach. I think it's actually running next semester, but anyway. So, here we go. What's happened is that I've added a 42. Okay, 42 should be to the left of 1138, so it's its left child. And then I try to add 2001. And it, right. So where would 50 go? So if the number we're looking for is less than the one we're at, we go left. Correct. We'd in fact go right here. So it would be the right child of 42. We don't actually shift nodes down. We leave the tree as is, and we just add things in their right spot. So in fact, let me do this in a drawing. Okay, so we've got up the top here, say 138, and it has 2 children. We go to add 20, it'll go to the left, so we'll now have 20, and then we go to add 34, if we go to add 10, well, that's going to be to the left child of 20. If we go to add 200, that's the right child of 138. And we build up that tree like so. So, '67 would be the left child of 200. I've run out of space, damn it, but it's, yeah, would be left child of 200. So these are really good if you are So, okay, let's think about the algorithm here. Left. Oh, hang on. No, you are right. You are absolutely right. Because at the top here, we go left. Left, then right shoulder of 34. You're correct. I was wrong. Yep. Okay, so that's trees. Quite handy. But really, they're just linked lists with two connections instead of just one. Okay. Okay, so last thing, definitely, is looking at the comparison of performance. So we often compare in terms of, for example, the amount of memory required. So a tree requires an additional pointer. What's missing from all of this, of course, from this description here, is the stuff that Biana talked about pointers. If you have an excessive number of pointers in your data structure, each one of them might be a cache miss, and they might slow down your access by an order of magnitude. So that's not talked about here. But really, we've got an unordered array. So insertion time, easy. Just insert at the end. Done. Ordered array, we have to search for insertion point and then insert it. Unordered linked list, just add it at the start or at the end. Well, at the start, because if you don't already have a pointer to the end, that's a problem. An ordered linked list, we've got to find the insertion point. By the way, if you need to keep your data ordered, an array is much better than a list. And then a binary search tree. Search is logarithmic because at each point we cut out half the search space. Right? So if I'm looking for the number 34, I can already discount the right side of the tree, right? Therefore, I only have to look at and every node I come to, I discount half the search space until I come to the node I'm after. Of course, if you insert items into a tree in sorted order, then they become a list. Right? So I'll just show you what I mean by that. Oh, absolutely. It is log n. Well, we could. Actually, that is a valid question we could ask. We could say, with a tree like this, 8, 5, 3, 6, 9, 11, 12. Ask you, you could, exactly. But I could ask you, okay, given this tree, an in order traversal, for example. So you go left as far as you can, because the leftmost bottom node will be the smallest. And then you go up. So we go 3, 5, 6, 8, 9, 11, 12. Say. We won't get you to do any code though. Okay, so that's the whole, that's all the material for today. Hopefully you got a lot out of it. Particularly the makefile stuff. So, any questions before we finish off? Yep, there's never a... The silly question is the one you didn't ask. It's fine. Yes, you are correct, Richard. If there are no negative numbers. So that's a problem. And there are various solutions to that problem, such as rebalancing the tree. So rotating the tree around so that the root is roughly halfway. Yeah, but a course around data structures should help with that, such as, well, we cover that to a certain extent in the C++ course. I'd like us to do it more, but yeah. No worries. Good luck on the next assignment.